Our military forces have grown over the years. However, the need for logistics support to provide a vital lifeline to the troops ashore has never changed. Modern military forces require a vast array of fighting equipment that must be available at the right place, at the right time, and in the quantities required. The Elevated Causeway System, or ELCAS, is designed to provide vital containerized logistic support to our Joint Expeditionary Forces. Where port facilities have been damaged, are non-existent, or where surf conditions, beach gradient, or other hydrographic conditions preclude direct discharge of cargo and equipment ashore, the ELCAS provides the ability to offload containers from lighters beyond the surf zone and quickly move the cargo ashore via wheeled vehicles. The mission of the ELCAS is to provide logistic support to Joint Expeditionary Forces during the assault follow-on echelon, logistics over the shore, and joint combined logistics over the shore operations. The ELCAS is a temporary pierhead and roadway made from connected ISO-compatible 40-foot steel pontoons elevated on piles extending seaward across the surf zone up to 3,000 feet from the beach. The pier length is determined by the draft of the watercraft you expect to load or offload from the pierhead. The underside of the pierhead and roadway structure must be installed to a minimum of 7 feet above the mean high tide water level to protect against higher sea states. Amphibious Construction Battalion personnel are assigned to support the elevated causeway. Personnel consisting of an officer in charge, assistant officer in charge, plus 76 crew members are required for each 12-hour shift, not including watercraft personnel. The goal is to build the complete ELCAS in 168 hours. However, experience has taught us that it normally takes over 3 weeks to complete with double shifts, 24 hours a day, 7 days a week. When the decision is made to employ the elevated causeway system and a general location has been identified, a site survey is required to determine the exact location of the ELCAS installation site. The primary requirements for site selection are: can the pierhead be located beyond the surf zone? The pierhead must have a minimum low water mark depth of no less than 12 feet. The bottom of the roadway and pierhead pontoons must be at least 7 feet above the high water mark to better survive storms. An acceptable beach gradient for beach ramp installation and 5-wide barge ferry landings. A nearby area to permit construction of the marshalling yard. An area that will not require pile to be driven into rock or coral. An area that can handle a reasonable flow of traffic in the beach area and in close proximity to a road network. The ELCAS is loaded aboard a Navy crane ship or commercial container ship in the reverse order that it will be offloaded. The majority of the ELCAS components are designed to be either ISO-compatible or capable of being stored and transported in ISO containers. The warping tugs, causeway ferry power modules, and ELCAS pontoons that will be used to build the 2 5-wide barge ferries will be offloaded first. The 5-wide consists of 15 pontoons, 5 pontoons wide and 3 pontoons long. The pontoons will be offloaded 5 pontoons at a time, then flexed together in the water alongside the ship to make up the 2 5-wide barge ferries. All ELCAS components must be offloaded from the transport ship anchored offshore and delivered to the beach via the 2 5-wide barge ferries. The total dimension of the barge ferry is 40 feet wide by 120 feet long. The barge ferries are propelled by a causeway ferry power module or warping tug. The 5-wide barge ferries are designed to carry 498,000 pounds or 249 tons of cargo. They are suitable for transporting ELCAS pontoons, 20-foot ISO containers, pile bins, 200-ton cargo cranes, and the 65-ton mobile crane from the transport ship to the beach or vice versa. An ELCAS interface frame is required to facilitate connecting the warping tug or causeway ferry power module to the 5-wide barge ferry. The ELCAS interface frame, or EIF, is a rectangular steel structure weighing approximately 12 tons and is attached to the stern deck of a 5-wide barge ferry and the bow of the warping tug or causeway ferry power module. Cargo loading of the 5-wide barge ferries is based on the pier installation sequence. The installation sequence determines the operational requirement for each barge ferry load. Proper loading of the ferries and securing the cargo on deck are critical to safe operations. For each barge ferry trip, one warping tug or causeway ferry power module will propel the barge ferry from the stern, and the second craft will be on standby to assist in propelling, maneuvering, salvage, and for safety purposes in the event of a casualty. After all components are ferried ashore, the 2 barge ferries will be disassembled and the pontoons used to complete installation of the ELCAS pierhead if needed. The marshalling yard is the center of all pier construction activities, beginning with barge ferry unloading operations. The yard is arranged so that equipment can move rapidly without disrupting other ongoing ELCAS activities. Pontoons, containers, equipment, and material are staged in pre-designated locations as they are delivered using the rough terrain container handler or the forklift truck. The marshalling yard layout must include 6 specific areas: pontoon staging and beach ramp installation, pile welding, pontoon storage, ISO containers, pile bin storage, mobile equipment storage and service. The marshalling yard supports the offloading of the barge ferries, provides storage and staging areas for the equipment and the materials used in building the ELCAS. Within the marshalling yard, the pontoon and pile storage areas differ from the staging area. As barge ferries deliver the pontoons and piles ashore, they are transported to their assigned storage areas, inspected for damage, and stored until needed for construction. When needed for construction, the pontoons and piles are moved from their storage areas to the staging areas, which contain the next components to be installed onto the ELCAS. When pontoons arrive in the staging area, the marshalling yard crew prepares the pontoon for installation by mounting connectors and other hardware that will facilitate pontoon connection in the roadway or pierhead. All preparation work on the steel piles are done in the pile welding area, so they are ready for use when delivered to the staging area. Piles are generally 38, 57, and 76 feet long and are 24 inches in diameter and 1/2 inch thick. There are 6 types of pontoons used to construct the ELCAS pier system. The general pontoons, used on the beach ramp, roadway, and pierhead. The spud-well pontoons are only used on the pierhead. The fender pontoons are used on the pierhead fender section. Center-raked pontoons are primarily used to build the 5-wide causeway ferry, but can also be used on the pierhead if needed. Left and right raked pontoons are no longer used to build the 5-wide causeway ferry, but can be used on the pierhead if needed. Beach matting is installed to ensure the unimpeded mobility of vehicles as they embark or disembark the barge ferries or ELCAS roadway. The ELCAS uses 2 types of matting: Unimat, which is fire retardant and used in the pile welding area. All other areas use Durabase, a durable plastic compound. There are 6 marshalling yard light assemblies independently positioned as required. Each generator can power a maximum of 3 light assemblies. Any area of the marshalling yard requiring illumination beyond 500 feet from the generator may use a floodlight trailer. There are 5 system components that make up the ELCAS. Pontoons, pontoon connector system, 200-ton crawler cranes, pile, ancillary equipment. The ELCAS pier system is constructed from 40-foot P40 series pontoons in an elevated position above the water by cantilevering pontoons from previously installed pontoons. The pontoons are supported above the surf on 24-inch diameter steel piles. This installation process provides a stable work environment because the ELCAS is above the water surface, allowing construction to proceed without interference up to and including Sea State 3. The pier system installation process begins from the beach and has 4 phases. The first phase is beach ramp installation. The second is the roadway installation. The third phase is pierhead installation, and the fourth phase is fendering installation. Following installation of the first beach ramp section, all pontoons of the ELCAS are initially cantilevered. Installation of the second beach ramp section entails cantilevering one pontoon at a time. During roadway and pierhead construction, pontoons are cantilevered off the ends of previously installed pontoons one at a time. Also during pierhead construction, pontoons are cantilevered off the sides of previously installed pontoons. Each installation phase uses the same basic construction sequence. Using the 200-ton crane, pontoons are extended in a cantilevered fashion, and then the support piles are driven through spud wells attached to the outside pontoons. The cantilevered pontoons are then leveled and secured to the piles using a pile gripper. The crane moves seaward on the newly installed pontoons and repeats the sequence. The pontoon connector system is designed to be capable of joining pontoons together side to side and end to end. The connector system enables rapid assembly and disassembly of the pier system and the 5-wide barge ferries. The connector system also allows removal and replacement of pontoons from the pier system should pontoons incur damage which threatens the integrity of the facility. The ELCAS connector system is made up of 3 basic types of connectors. Pontoon connectors join pierhead, roadway, beach ramp, and barge ferry pontoons side to side and end to end. These connectors allow the ramp roadway and pierhead pontoons to cantilever when connected end to end to installed pontoons. The angled beach ramp connectors are a unique component that is only used to connect the first roadway section to the beach ramp sections. The beach ramp connector provides angled connectors at the ramp breakover to allow for horizontal alignment of the roadway with the 7.5-degree angle of the ramp. Link connectors are used to connect the raked ends of the P40F fender pontoons to one another. These connectors provide for hinged connections that allow for relative movement between fender pontoons resulting from wave action. The pontoon sides and end connector slots contain a chute bolt assembly at the top of the pontoon and a lower fixed pin at the bottom which secures the connectors to each pontoon. The pontoon connectors have a rectangular body and are fitted with connection fittings at the upper and lower ends. The upper connection fittings are made of 2 sets of holes symmetrically located in the upper jaw plates to accept chute bolt pins from the 2 pontoons being connected. The 2 crawler cranes are used to conduct primary lifting and handling during the pier system installation and retrieval modes. The 200-ton cranes are capable of being transported on the deck of a Navy crane ship following the removal of the booms and counterweights. During ELCAS operations, the cranes are used to lift 20 and 40-foot containers and vehicles from lighters moored along both sides of the pierhead. The containers are lifted and placed on trucks parked on one of 2 pierhead turntables. Pile is used to support the elevated causeway. Primarily, 76-foot piles are required to support the ELCAS pier system at a suitable elevation above the water. For this reason, it is necessary to assemble pile strings from 2 38-foot pile sections provided with the system. Welding of the 2 pile sections requires a stable work environment. A 100-foot by 100-foot pile welding area is established for this purpose and provides 3 pile welding stations. Each of the pile welding stations is supported on unimat bases. The 3 welding stations are laid out in a U-shaped arrangement with the 65-ton utility crane positioned in the middle. This allows the utility crane to handle the 38-foot pile sections as well as the completed 76-foot lengths for each station without the delay of repositioning. Ancillary support equipment includes a 65-ton mobile crane primarily used to assist pile welding operations in the marshalling yard, an extendable boom forklift used to unload hardware and components from the 20-foot ISO containers and transfer those items to the work areas. In addition, the extendable boom forklift assists in staging pontoon connectors and external spud wells. A rough terrain forklift primarily used to transport palletized hardware and components in the marshalling yard, and finally 2 rough terrain container handlers, or ratch, used to move pontoons, pile bins, 76-foot pile strings, and 20-foot ISO containers. The elevated causeway construction commences with the beach ramp installation and concludes with completion of pier head and pier system outfitting. Concentrated ongoing activities of unloading, transporting, lifting, pile driving, connecting pontoons, installation of lighting, safety and navigation components, and cargo handling equipment all require knowledge, teamwork, and awareness of all applicable safety precautions. The pier can be constructed to a total length of 3,000 feet, but it may be installed in shorter configurations by limiting the number of roadway sections. The 200-ton crawler crane must be assembled before using it in pier system installation. The crawler crane is offloaded in 3 main pieces: the main body, boom, and counterweights. The cranes are assembled in the marshalling yard, and when the first crane is fully assembled, it is positioned where the beach ramp will be installed. Pier components are delivered in sequence to support pier construction. The area of the pier under construction at a given time is called the work face. Location of the work face changes with the completion of each section of the ramp, roadway, or pier head. All pontoons are brought to the work face individually by the ratch. The ratch also delivers the pre-sized piles in a small pile bin and returns pile cutoffs to the welding area of the marshalling yard. The forklift truck and extendable boom forklift are used to transport the tool skid, compressor, welder, and external spud wells to the work face. Prior to installation, pontoons must be outfitted according to the type and their intended location on the ELCAS. Pontoon outfitting includes inspecting, lubricating moving parts, installing pontoon connectors and fenders, and inspecting spud well grippers. ELCAS installation is conducted by cantilevering pontoons end to end and side to side. Cantilevering is a process whereby pontoons are suspended from previously installed pontoons through the use of pontoon connectors. Cantilevering allows the ELCAS pier facility to be constructed from the beach, eliminating the safety concerns associated with in-water pier construction processes. The first beach ramp section will be located approximately 80 feet landward of the high tide watermark. A bulldozer will be used to dig out an area 28 feet across parallel to the high tide watermark. The dugout area must have a maximum depth of 3 feet and be angled seaward at approximately 7.5 degrees. The beach ramp is comprised of 6 P40G pontoons, 6 angled spud wells, and 6 piles. Starting at the beach, the ramp sections are constructed by lifting and placing a 3 pontoon section in the prepared hole. The first beach ramp section is a 3 pontoon lift and is installed by the 200-ton crawler crane. The section should rest at an approximate 7.5 degree angle. Once positioned, 4 angled spud wells will be installed and 4 38-foot piles will be stabbed through the spud wells and the piles driven. It is important to note that all piles are driven to a blow count of 37 blows per foot. In other words, the pile driver would hit the pile 37 times, and it would go down 1 foot or less at maximum power on the pile driver. The piles are driven to a minimum bearing capacity of 100 short tons. All pier system piles should be driven to a minimum embedment depth of 15 feet before beginning blow count. If piles are not driven to the appropriate blow count or the minimum embedment depth, damage to the ELCAS may occur. If a pile does not